Okay, this is the third part of the review guide. So we're going to go over the electromagnetic spectrum, energy, photons, and the photoelectric effect. So this first one starts with just ranking them from shortest to longest wavelength. So we're going to do short wavelength on this side and long wavelength on this side. Now remember, that's the opposite of the direction that we did in class. I just want you to make sure you know them in order. You can write them either way. But our shortest ones are gamma rays, and then X-rays, and then ultraviolet, and then visible, and then infrared, and then microwave, and then radio. And then within visible light, the shortest wave for visible light is indigo. And then, nope, it's violet. Let's go. Indigo, blue, green, yellow, orange, red. Honestly, I usually write it the other way. I start with red and go to violet, even if it's the reverse order. So that is there. So then also the highest and lowest frequency and energy. So if you have a small wave with a small frequency or a small wavelength, then your frequency is going to be really high. So this is high frequency. And if it's high frequency, that means it's high energy also. Because remember, E equals HF, so if F gets really big, then E is going to get big. So this end is low frequency and low energy. Sorry, no, I'm just writing right now. So you should be able to know them in order. If I ask you to rank things, or say like which one has longer wavelength or longer higher frequency or whatever, feel free to write that on your test in order, and then you can answer questions about it. It makes it easier sometimes. So then here, calculate the missing information for photons. One helpful thing will be on your equation sheet, you have these prefixes. So if you do not have these memorized, that's totally fine. They are on your answer sheet or on your equation sheet. So like this is micro, so micro is right here. That's 10 to the negative 6. So that means you can just do 576 times 10 to the negative 6 meters. And that will do that conversion for you. So this is the same as 576 times 10 to the negative 6 meters. So then to find frequency, I should have grabbed a piece of paper. To find frequency, you need to use the wavelength and the speed, because the speed is the speed of light. And so that's going to be 3 times 10 to the 8th. And so we're just going to grab a note card. So that's our equation to get between these two. So if you have wavelength and you're solving for frequency, you just divide that over. So this particular one will be 3 times 10 to the 8th over 576 times 10 to the negative 6. And then you end up with 5.21 times 10 to the 11. And this is all going to be in hertz. And then to get from here to here, you do E equals HF. I put joules here, so that means the H that you need to use is the 6.626 times 10 to the negative 34. And so if you're looking for energy, it'll be 6.626 times 10 to the negative 34. And your frequency will be the answer from this, which is 5.21 times 10 to the 11th. And that should give you 3.45 times 10 to the negative 22nd. So 3.45 times 10 to the negative 22nd. So then for the other ones, again, it's the same equations. The only difference is like this one, you have the frequency, you're looking for energy. It's gonna be the same way we did this one. This one, instead of doing V over lambda, you're gonna do V over F. So that means for this one, it's gonna be E equals 6.626 times 10 to the negative 34 times this. And if you look at your equation sheet, giga is 10 to the 9th. So it's gonna be times 109 times 10 to the 9th. So you multiply that and you get 7.22 times 10 to the negative 23rd. Then go the other way. You'd still V equals F lambda, but in this case I have the frequency, I'm looking for wavelength. So it's just gonna be V over frequency, just 3 times 10 to the 8th over 109 times 10 to the 9th. And so that ends up being 0.00275. So you can put it as 0.00275, or if you want to, you could write it in scientific notation and do 2.75 times 10 to the negative 123. Those are the same number. It just depends on which way you like it better. And then again, the last two, it's the same thing. The difference here is that this time you have energy, you're solving for frequency, so frequency is just going to be E over H. So 4.3 10 to the negative 17 divided by 6.626 is the negative 34, which ends up giving you 6.5 times 10 to the 16th. And then here to here, it's gonna be the same way as that one. So you do V over F, which is 3 times 10 to the 8th divided by the frequency that I got from here, which is your 6.5 times 10 to the 16, which gets you the 4.6 times 10 to the negative 9th. So those are all just using these two equations, just plugging in the one you know and finding the one that you don't. And then we have photoelectric effect. Okay, so the one that I didn't put on your equation sheet that I did put on your test, don't remember which way I wrote it. It's one of those two. But as you know, E equals HF. So those are the same thing. I don't remember which way it's written, but it means the same thing. So it means that the kinetic energy of the electrons that are ejected off of the metal is equal to the initial energy of the photon, which you could write as E or as HF, minus the work function, which is the amount of energy that it takes to actually knock the electron off of the metal. So let's do an example. So a photon with enough energy, 5.1 electron volts of energy, will eject an electron from a piece of gold. So what that tells you is that is the work function. That's how much energy it takes to knock off the electron. What frequency and wavelength does light with this energy have? So it gives you the conversion. So I have an energy of 5.1 electron volts. I'm looking for frequency and wavelength. This is going to be exactly the same as the ones we just did. So the first one equals HF. Now this one is in electron volts instead of in joules. So it's the same problem, but I'm going to use the other value for H. So instead of using the 6.626, sorry, this is one of my deformed equation sheets. Instead of using that one, I'm going to use this one. So the 4.14. So I'm going to divide H over to find frequency. So my frequency is going to be 5.1 divided by, and then I use the H, the other H, the 4.14 times 10 to the negative 15. So then when I do that division, I get 1.23 times 10 to the positive 15. It was on the bottom and it was negative, so when you move it up, it turns positive. And that's going to be in hertz. Okay. Now technically that should be 1.2 times 10 to the 15 to be with correct sig figs. So I have frequency, and then to find wavelength, I do V equals F lambda. So I just divide my frequency over. So 3 times 10 to the 8th divided by 1.23. I do want to use the not rounded number there if possible. So I get 2.435 times 10 to the negative 7. So you can write that answer two ways. We do need to round it to 2 sig figs. So it's either going to be 2.4 times 10 to the negative 7 meters, or this is the visible light range. So if you would like, well, at least it's close. If you want to make it 240 nanometers, that is also acceptable. So those are both right. Just depends on which way you want to write it. You're probably going to write it that way, which is totally fine. So that is the energy of the very smallest amount of energy you would have to put in to get an electron to be knocked off. So then it says, what would happen if you were to shine a light of 6.5 electron volt on the gold surface? What would the kinetic energy of the released electrons be? So as long as this number is bigger than this number, it's going to knock electrons off. So now the rest of the energy, so 6.5 hits the gold. 5.1 of that energy is used to remove the electron from the surface. The rest of the energy is going to be left in the, in the electrons that are knocked off. That's where this equation comes in. So it says, what would the kinetic energy be? The work function we know is 5.1 eV. So we're going to shine 6.5 eV on it. So if this is all in electron volts, it's super easy. We just do K equals E minus psi. I think that's a psi. So it's 6.5 minus 5.1, 1.4. That's it. Okay. So then it says, what would happen if you used a light of 3 electron volts? The answer is nothing. Nothing would happen because it's not enough energy to do anything. So you have to meet that minimum energy to make any electrons come off. You can shine that light as bright as you want, and if the photons of energy are not big enough, no electrons will be knocked off. So that's one way of looking at it. Here's another one. So you get the information in a slightly different way this time. So let's look at it this way. So this is just giving you kind of a summary of what this experiment is. It gives you a little drawing. So what we have here is we have a wavelength of 240 nanometers. It says the battery voltage is increased until the current drops to 0. Really, that just means you've made the battery energy equal the energy that the electrons have. It's kind of another way of thinking about it. So the battery is pushing against it. So you're going to figure out how much does the battery have to push to keep the electrons from making that gap. We'll get more into electricity later, next quarter. But basically, that's why I told you here, the kinetic energy of the electrons is 1.4 electron volts. So first of all, we want to find energy in the photons. So we have a wavelength, 240 nanometers. We're looking for energy. Now we don't have an equation that has energy in it. We have an equation that has frequency in it. If you want, what you can do, I'll show you both ways and I'll just pick one to do. So you have V equals F lambda and you have E equals HF. If you want to, you can actually solve this for F. Okay, and then plug this in for this, and you get H times V over lambda. So if you would like to, you can do it in one step, or you can do it in 2 steps. It doesn't matter, but you're going to use the 4.14 times 10 to the negative 15th. You're going to use the 3 times 10 to the 8th as your velocity. And your wavelength is 240 nanometers. You need that to be in meters. And so you're going to do nano is on your equation sheet down here. So nanometers is 10 to the negative 9th. So we're going to call that 240 times 10 to the negative 9th meters. So if you do that, you get 5.18 electron volts. Now, if you want to, you can also first find frequency, which is going to be 3 times 10 to the 8th over the 240. If you do that, you get, let's see, I have it somewhere, 1.25 times 10 to the 15 hertz. And then you can do E equals HF, which is 4.14 times 10 to the negative 15th times 1.25 times 10 to the 15th. That should give you exactly the same answer. So it doesn't matter which way you do it. You can do it in one step or two. Just show me what you're doing so that if you mess something up, I can tell what you did. There's a lot of pieces to this, so if you do something little, like type it in your calculator wrong, for instance, then as long as you're showing me what you're doing, you're going to get most of the points. Okay, so just make sure you're showing me the work where I can follow it. Your answer is going to be 5.18 electron volts. So then it says, what is the work function? So the work function is in this equation. This is the work function. So we have K because we know that the electrons have 1.4 electron volts. And we know that the energy of the photons is 5.18. And so this is going to be equal to E minus K. So it's like how much of this energy is needed to knock the electrons off, and how much of it is left on the electrons. So we have 5.18 minus 1.4. I get about 3.78. And that is in electron volts. So then the last one says, what's the longest wavelength that would cause electrons to be emitted? So essentially, you're looking for what wavelength would give the ejected electrons 0 kinetic energy. It would knock them off, but it wouldn't go anywhere. So you really want to see at what point is the work function equal to the energy, so that there's no leftover energy. You just knocked it off, and that's it. And so then you can just do HF to find the work function, and you can relate that to the frequency of the photon that it would take just to get you enough energy to knock it off. So the frequency is going to be E over H, which is going to be, the work function, I'm going to use 3.775. It's like the not rounded number. So if you divide that by 4.14 times 10 to the negative 15th, that gives you 9.118 times 10 to the 14th. Keep extra digits if you can, because we're not done yet. So then you take that frequency and figure out, well, for that frequency, what's the wavelength going to be? So we divide our frequency over, and our wavelength is going to be 3 times 10 to the 8th divided by the frequency. Again, more digits is better if you're in the middle of the problem. And then that gives you 3.29 times 10 to the negative 7, which would also be 329 nanometers, depending on which way you like it. And so that's the longest wavelength, because long wavelengths are low energy. So any longer than that, and you won't have enough energy to knock off the electron. Okay? So that is the last 2 pages of the review guide. And then you should be good to go.